This is section 6.4, vectors. It's going to feel like we have totally changed directions for a little while. We're going to have to learn a lot of definitions and a lot of notation before we can go on. Trig does come into it later in the section, but we have a lot to build up to before we get there. So let's just start with some definitions and notations. In the physical world, many quantities such as length, area, mass, temperature, and so on are completely described by their magnitudes in appropriate units. So if you want to describe the temperature as 75 degrees Fahrenheit, you've done it, you've described it. And those quantities that are just can be described completely by a number are called scalar quantities. Other physical measurements like velocity, acceleration, and force require more information. These require both a magnitude, which is a size or the numerical value, and a direction to be completely described. So pushing something with a force of 5 foot-pounds or whatever your measurement is, it doesn't tell you anything unless you know which way the force is being applied, whether you're trying to move something left or right. The direction is important. When you have a measurement that requires both a magnitude and a direction, those are called vectors and vector quantities. Where we are going with this is we're going to start doing operations like something analogous to addition, subtraction, multiplication, division, so on, using vectors. And the math is not the same as the arithmetic you learned in elementary school, but it has a lot of similarities. And it's going to be important with the notation that we are able to distinguish between these. And if you are not careful when you're writing things down, and you don't make the distinction between a vector and a scalar, you can really mess things up. So make sure you're getting this notation, okay? Now, a vector is described geometrically by a directed line segment with an arrow at one end. So it looks something like this. Now, in geometry, we tend to call that a ray, but we're talking about physical forces and things, so we're talking about vectors right now. The arrow specifies the direction, so it's being pushed in that direction. That's the direction it is going. The length of the arrow describes the magnitude. So the longer the arrow, the more force is being applied, or whatever physical measurement you're talking about here. The tip right here, where it starts, we call the initial point, and wherever the arrow ends is called the terminal point. Now, in print, vectors are usually represented by lowercase, bold-face type. We tend to use A, B, I, J, U, V, and W. I don't know why these are the traditional go-to variables for vectors, but they are. Okay, specifically I, J, and then when you get into calculus 3, K. But don't worry about that right now. Now, when handwriting, we can't write bold. So when we're drawing, using a variable for a vector, we usually draw an arrow over the top. And sometimes we get lazy and draw sort of a half arrow, so we don't put the whole arrow on the end. But you just definitely need to make a distinction that you're talking about a variable, a vector, by putting some mark over it. Now, when we're in the world of vectors, okay, we refer to real numbers as scalars. So anything that can be measured by simply a value, a numerical value, is a scalar. In print, like in your textbook or online, scalars are usually represented by lowercase italic variables. Now, by writing by hand, we usually just write simple lowercase letters. So I think you can see why, if you have a vector A and you had a scalar A, you would need to distinguish between the two, because the way you work with the arithmetic of these is very dependent on whether you have a vector or a scalar. Okay, so let's look at this. Let's say if we're just going to have, this could be a vector, P would be our initial point, and Q is our terminal point, okay? Instead of writing just the vector V in boldface, we can write the vector as PQ with an arrow over it. Now, it's important that the first letter here refers to the initial point, and then it ends at the terminal point. You're just basically drawing the arrow in the same order as here. Okay? Now, we talked about how the length of the vector drawn is the magnitude. Another word for the magnitude is called the norm. And the norm of a vector, PQ, is denoted, it looks a lot like an absolute value, but it's got doubles. And it turns out that norms and absolute values are kind of related. We'll get to that more in a second. We'll talk about how to calculate these. But if you see the double, what looks like double absolute value, you're being asked to find the magnitude or the norm. Okay? Now, equivalent vectors. Equivalent vectors have the same length and direction. And as vectors are defined only by their length and direction, equivalent vectors do not have to be in the same position. So basically what this is saying is if you were talking about vectors being in a coordinate system, if I had this one, and they both point the same direction, or in algebraic terms, if they have the same slope, and or pointing in the same direction, and they have the same length, then they would be equivalent. It doesn't matter that they are in different locations. So here are your basic possibilities. And if they are equivalent, we put an equal sign between them. Here we have vector v and vector w. They have the same length. They are in the same direction, so they are equivalent. Here, they have the same direction, but they have different lengths, so they are not equivalent. Here, our vectors appear parallel, like here. They have the same length as in here, but if you look at the arrows, they're pointing in opposite directions, so they are not equal. And here, our vectors they are not the same direction, they're not the same length, there's nothing here that indicates that they could even remotely be equivalent. Okay, now, we also have a vector of length 0. And that is called a zero vector, and it is denoted by a bold 0 or a 0 with an arrow over it. The zero vector has 0 magnitude and an arbitrary direction. Again, vectors and scalars operate differently, so it is critical that you distinguish between a zero vector and the scalar number 0. Our arithmetic changes completely of whether we are dealing with a vector or a scalar. Okay, now specifically in the case right here, where everything appears to be the same except they're pointing in opposite directions, when we have two vectors that are the same length but opposite directions, we say that in this case these are labeled v and a. A is the opposite vector of v, and very similarly to what we did in algebra, we would write that a is equal to negative v.